So I'm going to go through a series on classical mechanics, which will be based off of John R. Taylor's classical mechanics textbook. Now, with classical mechanics, it's really interesting because a lot of people who get into physics, I feel, mostly get into physics because they think quantum mechanics is super cool, or they think relativity is super cool, and mechanics is kind of like supposed to be the boring class, I guess. It's not, as popular in mainstream culture, I guess, as some of these other courses. But mechanics is actually a super, super interesting class. It's super practical. Something like relativity, really you only need it when you get very close to the speed of light. With quantum mechanics, you only need it when you're dealing with really, really small things. So this is a really applicable course. So I'm going to go through and talk about the different sections, the different chapters, and talk about it a little bit and highlight the points that I think are really important. So I'm going to go ahead and start at 1.2, which is space and time. And I might not cover every single section, but I'm going to try to cover most of them. Some of the ones are not, I don't think, too important, but we'll cover a good bit of it. So I'm going to draw a three-dimensional graph, which, if you're not okay with yet, highly recommend you get comfortable with the idea of three-dimensional graphs and multivariables, that sort of thing. Now, if you've taken multivariable calculus, sometimes they call different things X, Y, and Z and whatnot. And it can be kind of confusing. I'm just going to call this Z, this X, and this Y. Sometimes you see Z pointing out at you. X is out here. Sometimes I'll highlight it. I have to remember you guys can't see my pencil. Sometimes X is along the Y-axis, Y is along the Z-axis, and Z is pointing along the X-axis. Depending if you're working with physics or you're working with math, this is one interpretation. So let's say we have some random point here, and I'll use red. Why not? Let's say we have point P. Now, this can be, first off, let's talk about how we get there. The way you get there is you go some distance along, you walk along the x-axis, then you go some distance in the y-axis, and then you go some distance up in the z-axis. So this is, this is going a distance y, this is a distance x, this is a distance z, if that makes sense. And we can label this point as just being the point x, y, z. We can also think of it in terms of a position vector. So if we go from the origin, which is just right here in the center, 0, 0, 0, pointing to the area in interest, we can think of that as a position vector r. So maybe I should make a note on that as a key point. R is a position vector. Let's change up the colors a little bit. We'll go with black. Now, what does it tell us? This tells us the distance and direction from the origin to P. So I'll make that note here. Let me make the size a little bit bigger. That might help. Okay, so this tells us the distance and the direction from the origin, which I'm going to call O, that's there, that's 0, 0, 0, to the point P. So not too much to say there. If we look at the components, this XYZ part right here, This is the components of our R vector. It has a component in the x direction, it has a component in the y direction, and a component in the z direction. The unit vectors, that deserves its own color. The unit vectors are just x hat, y hat, z hat. So usually the way we can denote this is r, your position vector, is equal to x hat, plus your y hat, plus z hat, where these guys are unit vectors pointing in the direction that we're going. And sometimes you see it written like this. Sometimes you'll see it written like this, where r is just x I hat plus y j hat plus z k hat. I guess just writing x and y and z kind of over and over again got a little redundant, so they're like, well, we'll change it up, I suppose. So let's look at a few examples. And come over here. Let's look at a velocity vector. So a velocity vector, let's call it v. That will have components. Shouldn't put equals, but I'll just say it has components. Velocity in the x direction, velocity in the y direction, velocity in the z direction, something we're really interested in. Okay? If we were to look at an acceleration vector, I'll put arrows so we know we're talking about its components. Same exact thing. I'm going to stop putting these little arrows indicate that it's a vector. Sometimes a vector is denoted as just being bold, but that's kind of hard to do if you don't have a font. And so just know that these are vectors because I'll get lazy. Okay, so let's look at two vectors. Let's look at vector r. Let's say vector r is just r, we'll just say r1, comma r2, comma r3. And we'll say there's a vector we'll call s, which is the same thing, s1, s2, and s3. Now, if we have those vectors, if we want to add vector r plus vector s, well, it's pretty straightforward. It's just multiplying, or not multiplying, adding the like components. And there you go. You just have to add your x components, your y components, and your z components. So pretty straightforward there. This can be helpful if you think about it in a physics sense. So let's say you have some object that has some force being applied to it. We can just add vectors very easily. So the total force, let's say force A and force B we're adding on it. And the total force is just the force by A plus the force by B. So that would be kind of a physics example, I suppose. Another one that is important to know is if C is some constant. If C is some constant, then C sub R, using the same R we had up there, you just multiply it to each component. So pretty straightforward. You can distribute the C into each component of R, basically. Go ahead and talk about the dot product. So this is one way we can multiply vectors, is the dot product. This dot here is kind of how we denounce that, and that is equivalent to the magnitude of R times the magnitude of s, that's what those little bars mean, times cosine of the angles between those two vectors. So let's say we have something like this. This is vector r. This is vector s. This is our theta that we're interested in. The other one I want to talk about is the cross product, which is r cross s. Looks very similar at first, except instead of cosine, it's sine of the angle between them, and we add this n hat. So let's make a note of something real quick. Let's note that our dot product, what I just highlighted in yellow, that spits out a scalar, not a vector. The cross product, I'll highlight that in green, does not spit out a scalar. That spits out another vector. And this n hat, this unit vector, is kind of what gives us our vector back. Now, the way that works is, let's say we have vector r, vector s, here's our theta. Now this n vector, oops, there we go. This n vector right here, that's going to be perpendicular to both r and s. And no matter how you try to find another perpendicular vector for those two or a third perpendicular vector to r and s, the only way you're going to be able to do that is if you introduce the idea of a vector going into the page. What's into the page is like this. It's kind of like an arrow. This implies it's going into the page, like you're looking at the back of the arrow. This dot implies it's coming out of the page. So the only way you could be perpendicular to those is in that case. So which one is it? Well, that's just by the right hand rule. So you'd place your fingers in the direction of, we'll use a different color here. So R, right? We place our fingers in the direction of R. And we want our hand placement in such a way that if we curl our fingers, it curls towards S. So if you place your fingers along R, right? If you placed your fingers there, how could you curl your fingers to go towards S? Well, the only way you'll do that is if your thumb is pointing down. And that's the direction that our N is pointing. So that is our dot product. That is a cross product. Quick example of dot product. We can look at work, right? Because work is force times dr, where these are both vectors. An example for cross product would be torque, right? Because we know torque is R cross F. And all three of these guys are vectors. So it comes up in physics quite a bit. To find the magnitude of a vector, say the magnitude of R, that's just the square root of R1 squared plus R2 squared plus R3 squared. Hopefully you guys know this, but I'll mention it because maybe it's helpful. One other thing I want to mention about the cross product. So with the cross product, let's say we have P equals R cross S. There's two ways to kind of interpret this. There is the X component, that's a bad arrow, of P is RY SZ minus RZ SY. The Y component is RZ SX minus RX SZ. And the Z component is RX SY minus RY SX. Now, I don't always remember that, so what I tend to do is just find the determinant, which is, we'll set it up real quick. Rx, Ry, Rz, Sx, Sy, and Sc. And if you solve this, you'll get this for your x component, this for your y, this for your z. The way I usually do it is, if I'm interested in the x component, let me make that a little nicer. If I'm interested in this bit, right, I cover this, and then you can just do Cramer's rule, where it's this times this minus this times this. And if you do the y, if we wanted to do the y, for example, lost my x, then we cross this. This is still crossed. And then it's this times this minus this times this. So it might be helpful to brush up on determinants if you're not already. And real quick, I just want to talk a little bit about taking derivatives of vectors. So real quick, velocity is just the derivative of our position vector. And acceleration is just the derivative of our velocity. And then the quick definition, dx by dt is the limit as delta t approaches 0 for delta x over delta t. And kind of using that same logic, dr by dt is just equal to the limit as delta t approaches, not equals, 0 of delta r by delta t. So just a little Calc 1 review here. I would be comfortable with this, just as what's about to come. You've probably taken a first-year physics course, and you know Newton's second law, but it can also be thought of like this. Or, same thing right here. Now we have a differential equation. So that is something to be familiar with. A few rules with derivatives. The time derivative of, these are vectors, these are all calculus on vectors. Nicely, it just distributes over addition. Right. Real quick, product rule. So let's say you want to take the derivative with respect to time of f of x, g of x, that's f prime g plus f g prime. So a product rule reminder. Likewise, if, let's say we have r equals x hat plus y hat plus z hat, then the derivative of r with respect to t is dx dt x hat plus dy dt y hat plus dz dt z hat. So you just take the derivative of x and y and z. The important thing that should be noted here is that our unit vectors x hat, y hat, z hat are constants, which means, I guess I'll write this out here. d by dt of a constant times f of x is just c f prime of x. So we can factor out that constant. So these can just be factored out and distributed after we take our derivative. That's not the case. So in polar, for example, in polar coordinates, be careful. That's what I'll say. Just be careful. We're not there at polar coordinates yet, but it is a note to make that these guys are constants. sometimes your unit vectors will not be constant, and you have to be careful with these derivatives. But these guys are constants, so we can get away with it. So that was just a little math review, vector review kind of thrown in. It's the boring part, but that's how every physics course really starts, and we have to get it out of the way. So we got that done, and we'll get into more and more fun things soon.